There is an option called present now. Just behind your mic option, sir, right side. Turn on captions. After that, there is an option called present now.
There it has been written admin 3 is presenting.
Okay,
That
you
one?
just yes sir, yes sir. And presently admin 3 is presenting your slide, sir. After stop presenting, I will guide you how to present, sir.
Okay,
After a small introduction.
Sure.
Okay, sir. Thank you, sir. So, a very good morning to one and all. Myself, Rajastri, Research Scholar, EC Department, NIT Puducherry, welcome you all for the day 4 of 5-day national workshop in advancements in antenna engineering using artificial intelligence. It is my great honor to introduce the resource person, respected Dr. Amalendra Patnaik, sir, Associate Professor, Department of ECE, IIT Roorkee. He completed his PhD in Design Optimization of Planar Antennas using ANN techniques at Berhampur University, India in 2003. His research area includes RF and microwave engineering, machine learning applications in electromagnetics, CAD of antenna, plasmonic antennas. He served as the investigator for several funded R&D projects. He has 10 research scholars are working under his guidance and 3 completed. He published a book titled Compact Antennas for High Data Rate Communication for Ultra-Wideband and MIMO Technology in Springer in 2018 and Engineering Electromagnetics in Adapted India edition. And also he published 2 book chapters. He has 41 research publications in the reputed journals and conferences. He chaired the Department Research Committee from 2017 to 2019 at the Department of ECE, IIT Roorkee. He is the senior member of IEEE. He won Distinguished Speaker in IEEE APS in 2015. International Union of Radio Science Young Scientist Award he won in 2005. And also he won IETE J.C. Bose Memorial Award in 2000. Not only this, he won a lot of awards. I welcome you, sir. Now I request Dr. Amalendra Patnaik, sir, to take over the session.
Thank you for that nice introduction. Let me share my slide first.
Thank you, sir. Sir, at the bottom right corner, there is an option now, sir. Present now.
The entire screen.
Yes, sir. After that, you click that screen and entire screen, and after that, you share that, sir. Yes, sir. It's visible, sir. Your PPT is visible. Thank you, sir.
Okay. Very good morning to all of you. For today's presentation, am I audible?
Yes, sir.
Yes, sir.
Yeah. For today's presentation, I have decided to keep the topic as meta heuristics in antenna engineering. Why and how? Why to use these techniques in antenna engineering? And after that, we'll decide how to use these techniques effectively to get proper results. If you see the dictionary, you will find the meaning of heuristics as to find or to discover by trial and error method. And meta means beyond or higher level. Like so meta heuristics is finding a solution by trial error method But that trial error method is not completely erratic. It's a systematic manner of finding out the solution. So heuristics is a way by trial or error to produce acceptable solutions, right, to a complex problem. And the important thing is in a reasonable practical time, within finite time, you should be able to get a reasonable or acceptable solution to a complex problem. Why complex problem? Because if you see the antenna engineering problems, there are cases where closed form formulas are available. So you put the value of the parameters, you will get the answer. But there are situations where it is difficult to get a closed form relationship between input and output. Or there are situations where it is difficult to find out a solution, right? So there we are taking the help of these meta heuristics techniques. The complexity of the problem of interest makes it impossible to search every possible solution or combination. So because of the complexity, it is not always possible to find out a reasonable solution. The aim is to find good feasible solution in an acceptable time scale. In particularly in, if you see in microwave engineering, you need to find out the solution in a time bound manner. Right? So most of these projects that has to be completed in a timely manner. So every task that you are attempting to be completed in specific time. So these techniques, if you study the literature, different people call it with different names. Some people call it as meta-heuristic techniques. And when the concept started, when people started using these techniques in antenna engineering, they started the term soft computing techniques, and they took this term from computer scientists, right? And other literature, they call it as evolutionary techniques, although it's a part of this meta heuristics. And this has been now extended to artificial intelligence techniques, right? So if you see this particular block diagram under the umbrella name of meta heuristics, you will find lot of methods of implementing those meta heuristics. And you can see, like some methods, most of these methods are population based, meaning you initially for solving a particular problem, you choose some specific solutions depending on the parameters, and with iterations you will find that these random solutions that you have chosen initially will gradually move or gradually approach towards the actual solution with some error tolerance. And again, you can mark that most of these techniques are naturally inspired. Like these techniques that people have developed by observing the uh, by observing the phenomena that are usually observed in nature. Okay. There are other techniques like local search techniques and trajectory based methods. Those methods are available. But as far as today's discussion is concerned, we will mostly focus on this population based methods or these evolutionary algorithms. Okay. Now, as I told you previously, people were calling this as soft computing techniques. Gradually, we coined different terms for these techniques. So, what are these subcomputing techniques? These are a family of methods, not a single method. It's a family of methods that imitate human intelligence with the goal of creating tools provided with some human-like capabilities, such as learning, reasoning, and decision making. Okay. These techniques can learn a particular thing, and with the help of reasoning, these techniques can take a decision, or in other words, they can produce an acceptable solution within a time limit. Okay. So if you study the literature, you will find, according to Professor Jade, the aim of soft computing is to exploit the tolerance of imprecision, because in engineering, in most of the cases, we are not looking for exact solutions, right? So by exploiting that particular tolerance of imprecision, uncertainty, approximate reasoning, and partial truth to achieve tractability, robustness, low cost solution. This particular thing is important. It's a low cost solution and close resemblance with human-like decision making. Like if you are observing 10 different things for the 11th particular task, you can take a proper decision by observing the outcomes of 10 different previous tasks, something like that. So we can use those particular things because in most of the cases we don't need the exact answers. So that particular thing can be used particularly in engineering to find out acceptable solutions. Now let us see how these techniques are different from hard computing. In soft computing techniques, it exploits the given tolerance of precision, partial truth, and uncertainty for a particular problem. Whereas in hard computing, we strive for exactness and for the full truth. You apply the formula available, you apply the integration, differentiation, those things, and try to find out the exact answer. But if you compare that with soft computing techniques, we are not moving towards that one. In case of soft computing, inductive reasoning plays a larger role. Inductive reasoning means by observing the outcomes of the previous problems, you can expect the outcome of the present problem, right? That is what is known as inductive reasoning. So it plays a larger role as far as these meta heuristics or soft computing techniques are there. Whereas in hard computing, inductive reasoning hardly plays a role. We are not going for using these techniques as far as hard computing is concerned. We are not going for applying inductive reasoning. Okay. So, for example, if you see, one is a Chrisman, another a fuzzy man, and what is the task? How are you going to park a car, right? So if you ask this question to a Chrisman, you will get an answer something like this. You have to switch to reverse, then push an accelerator for 3 minutes, 46 seconds, this, and finally you can park your car. But if you ask that to a fuzzy man, fuzzy logic, which is also coming under that soft computing techniques, he will give you a simple solution. It's easy. Just move slowly back and avoid any obstacles. That's all. So in both the cases, you will get the final answer or final solution. But here, if you see, we are not going for those exact measurements, exact timings, exact values. We are not going for that one, right? So in that way, these are easy process to get acceptable solution, and that too, the time of computation is not infinite, right? The within a limited time, you are going to have easy solutions. That is the reason why we are preferring not only microwave engineers. If you see engineers in other branches also, civil, mechanical, electrical, you will find the application of these meta heuristics or soft computing techniques. What are the key areas of this soft computing technique? Although every day, if you go through the transactions on the evolutionary computation technique and the neural network, those things, you will find every day new type of meta heuristics are coming into picture, right? People are framing new rules, new techniques to handle with complex problems. But the most widely used techniques that has been used to solve particularly microwave engineering problems or antenna problems are these particular things. You'll find a lot of applications of neural networks in antenna engineering. And as far as other optimization techniques are there, you can find the applications of genetic algorithm, fuzzy systems, ant colony optimization, bacteria foraging optimization, particle swarm optimization. Those things has been used in the antenna literature. So, like if you see the literature of like 90s, there people have started using the ANN technique first for solving antenna problems. Then gradually the other things came into picture, right? And nowadays, most of these particular techniques you will find as toolboxes in MATLABs and other RF simulators also. Like most of these present day RF simulators are coming with these optimizers, right? In MATLAB, you can find neural network toolbox, genetic algorithm toolbox, and those things are available. In CST, HFSS, other optimizers are also available. That means once you have designed your structure, to optimize that one, finally you choose that particular optimization so that you will get a optimized structure for your required results. Okay, so what exactly we are doing in this while applying these meta heuristics? We are basically searching for an acceptable solution for our problem. Okay? Or in other words, basically these are search techniques, right? So there are different search techniques available in mathematics. First one is calculus-based techniques. Second is enumerative techniques. And third one is guided random search techniques. So there is difference between random search techniques and guided random search technique. Okay. So in guided random search technique, there are rules of, although the starting point is random, but as you are approaching towards the result, the process is a completely guided one, right? There are rules how to choose the next solution, next better solution, and so on. So in each meta heuristic technique, specific rules are there to go from the initial random solutions to the final optimized solution, right? So most of these meta heuristics are coming under this guided random search techniques. So these evolutionary algorithms are a part of this guided random search techniques, and the other techniques like genetic algorithm, all other techniques that I showed you in the previous slide are coming under this particular branch, are coming under this guided random search technique branch. So to give you an example of these guided search techniques, in the initial step, basically it's the process is random, right? So for example, if it is a two-dimensional problem and you are in the process of finding out the solution in this particular case is to find out the maxima. So initially you are choosing the random solutions on this two-dimensional sort space. And see, this is for generation 0. So with iteration, in general, these are iterative techniques. Gradually, you will find that all these random solutions are approaching towards the maxima, right? So this is the global maxima as far as this particular problem is concerned. This is the local maxima, and there are methods available how to go, how to move from this local maxima to global maxima points. So all these meta heuristics are basically have this particular approach, right? So these are guided random search techniques. Why it is a random search? Because initially you are choosing the possible solutions. If it is an n-dimensional problem, in that n-dimensional solution space, you are randomly choosing those solutions, and with iterations, that means depending on the type of meta-heuristic that you are applying, you follow those particular guidelines, and with iterations, you will find that your the random solutions, all these random solutions are approaching towards the maxima or the minima problem, whatever the way you have formulated your problem. Okay. In general, we are these meta heuristics are techniques to solve a maximization or minimization problem, meaning the problem in your hand has to be converted to a maximization or minimization problem, right? So in antenna problem, suppose for example you want to find out the resonant frequency of a given antenna, right? So in general, it will depend on the dimensions of the antenna and other materials used in this those material properties. It will depend on that one, right? Now, see the function between these two. That means the output is your resonant frequency, input is the dimensional problems, materials, dimensional parameters and materials. Now, this particular relationship has to be formulated as a maximization problem or a minimization problem. Then only you can apply these heuristics, right? So, the point of discussing this particular thing is you first convert your problem to a maximization or minimization problem, then go for the use of this meta-heuristic techniques. So you can use any meta-heuristic technique, you can use any optimization technique, but if the task that you have to perform before applying the meta-heuristic technique is to convert your problem in hand to a maximization problem. So let us see a simple genetic algorithm problem. Now see, the starting point is initialize population, evaluate population, meaning you are choosing if it is a suppose 3-dimensional problem, in that 3-dimensional space you are choosing the random solutions, right? Random solutions means a possible solution, and the values of so if it is a 3-dimensional problem, you take specific values of those 3 variables, you find out the solution, right? So initially, in almost all these meta-heuristic techniques, you are choosing these solutions randomly, right? And you try to find out the new solutions in an iterative problem, in an iterative manner. So evaluate population, perform recombination mutation, evaluate population. So you keep on creating new solutions until the time you have not met your this termination criteria. So again, while applying these meta-heuristic techniques, you need to choose this termination criteria, meaning what is the error between the exact solution and the solution that you are thinking is acceptable as far as your problem is there, right? So you need to fix that particular criteria. Suppose, for example, your resonant frequency is 5 gigahertz, resonant frequency of an antenna, and by applying these metaheuristic techniques, suppose you got 5.0003. So here the tolerance limit is 0.0003. Okay, so the time you reach that particular criteria, then the iterative process will stop at that particular point. You will not find much difference between these two resonant frequencies. If that is acceptable to you, if at all it is acceptable to you, then your iterative process will stop at that particular point. So before applying that, the method of applying the metaheuristic technique is, first step, you need to convert your problem in hand to a maximization problem. Then you need to choose a proper termination criteria, because almost all of these methods are iterative technique. So somehow you need to stop these iterative techniques at some point of time. So how to do that? For that, you need to choose a termination criteria, right? So although I have given the name, I have discussed it with the genetic algorithm, but if you study the other metaheuristic techniques, you will find the general method is the same one, right? You need to first choose a particular method, then you need to convert your method to a maxima problem, then you need to choose a proper termination criteria. Okay. Now there are situations where although you suppose you have chosen a particular termination criteria, even apply number of iterations, there are situations you will not find your solution. Okay. So what exactly is happening in those particular cases? So even after applying thousands of iterations, 10,000s of iterations, if you are not able to meet your termination criteria or not able to get your solutions, meaning the iterative technique has been trapped at some local minima. Okay. So in that particular case, there are techniques available it will vary from one metaheuristic to other metaheuristic technique. So you need to tune some specific parameters of that method. There are tuning parameters available in each of these metaheuristic methods. So you first try to tune those parameters. If again, in some cases it will not work. Even if you tune those parameters, you will find that it is not working. Not working means even after applying quite a large number of iterations, you will not get the solution. Then the advice is you start the problem afresh, or in other words, you choose your random solutions that you have chosen initially in a new manner or at a new positions. Or in other words, you start the problem, you start applying the problem afresh. So although most of the time it is possible to get the solution as far as these meta heuristics are there, but rarely you are going to face this type of problems also, right? Because if you see this example, because see this one is a local maxima, whereas this is a global maxima, right? So with iterations, all these possible solutions should converge at this particular point, right? But in some cases, it may happen that you will find all are converging at this point, right? So in that case, the advice is to start choosing this initial population or initial random solutions again. Okay. So the same example, that was the general case. Here it is specific example. Suppose it is desired to find the maximum of pick of function of two variables. So it's a f is a function of two variables, x and y, and the range for x and y is given -3 to 3 for both the cases, right? So here you need to find out the pick of this particular function or the maximum of this particular function. The first step is to represent the problem variables as far as genetic algorithm is concerned. We are calling it as chromosomes. In other techniques, you will find other nomenclature for the variables. Okay. So randomly, because both the x and y are having -3 to 3 range, so in that space, and this is the f-axis. This is the x-axis. X is for y, is x is for f. So randomly you are choosing these functions, these solutions, and with iterations you will find for both x and y you are getting the maxima at this particular point. Okay, so at that point you choose what is your x, what is y, and that is the solution for this particular problem. Okay, so as I told you, rarely you may end up with this particular hill. Instead of reaching to the actual maxima, you may reach up to this point, right? And this example is a simple example, but there are situations where you will have n number of maximas, n number of minimas. So in those type of problems, particularly in antenna engineering, we are encountering those type of problems, having a lot of maximas, lot of minimas, right? So in those type of problems, if you are trapped in that iterative procedure, it's better to start afresh. If nothing is working, then better you start afresh. So although this is specific to genetic algorithm, but the general process of applying any meta-heuristic technique is similar only. Okay. So specify the problem, define constraints, and optimum criteria. Okay. Specified problem means the problem has to be properly defined. Defined means in this case when you are planning to use meta-heuristics, you convert that problem to a suitable maxima or minima problem. And define constants. You see what are the variables involved in that particular problem, what are the limits of that problem. Limits means, for example, if it is a microstrip antenna, yeah, and the substrate dielectric constant. So, like minimum you should fix at suppose 1.8 or 2, and maximum is 10 or 12. That should be the variable range as far as epsilon r is concerned, right? So for all the variables, you need to choose the range, and the constants. The other things is that from one method to other method, there are some tuning parameters available, and you need to fix those tuning parameters. Set rules are there for each of these meta-heuristics, and according to those rules, you need to choose the value of those tuning parameters. And the optimum criteria, you need to choose that the tolerance range for terminating the iterative process. Represent the problem domain as a chromosome. Here in genetic algorithm, we are calling it as chromosome. The third is define fitness function to evaluate the chromosome performance. So, for each problem you are trying to solve, you need to choose your fitness function properly, meaning that means suppose again let us see the same problem of finding out FR, resonant frequency. Then you need to have in every iteration of this meta-heuristics, you are going to get a particular value of FR, and that FR, the consecutive the difference between two consecutive FRs, if it is suppose within some limit, then stop my iterative process, something like that. Okay, so you will find that the fitness value, that means initially you have chosen the random solutions for your specific parameters, and during iteration all the parameters will change their values within their range, and each time you are going to get a new value for the output, and the error between the actual value and the present value, you will find that error is decreasing with the progress of these iterations. Okay. Then depending on the type of meta-heuristic that you are applying, you tune its parameter during its running process, right? So there are a few other meta-heuristic techniques where you can fix all those tuning parameters at the beginning, and there are other meta-heuristics where you can change those tuning parameters during its running phase, meaning you will find that after certain iterations, like 50 or 100 iterations, you will find that the process is becoming slower and slower. That means it is uh, the the time of approaching towards the exact solution is going larger and larger. So in that particular case, in certain meta heuristics, the tuning parameters can be changed so that the process will become faster. The process will become faster. Why these are important? Because in some cases, like if you want to solve a problem for a real-time application, there time plays a major role. You need to get the solution within a stipulated time, right? So in that particular case, the process has to give you the answer within that stipulated time, right? So as I told you, there are methods where you can fix these tuning parameters at the beginning of the iterative process, and there are other techniques where you can tune these parameters during its running phase. So most of these techniques, they follow similar processes, although we are discussing it with GA. So as I told you, you can find the application of these meta-heuristics, not only GA, all other meta-heuristics also in not only in microwave engineering or antenna engineering, but in other branches of engineering also. A lot of application has been done in signal processing. Nowadays, people are applying this to robotics, control system engineering. So in all, almost all branches of engineering, you will find the application of these meta-heuristics. Okay. Any question at this particular point? Then we will go for the next topic.
Any question from participants?
Participants, you may ask questions to the resource person.
Okay. If there are no questions, then I should continue. Then in antenna literature, you will find a lot of application of neural network technique. Okay. So let us discuss this technique. Then we will go for the discussion of how to apply these techniques effectively in antenna engineering. Okay, with examples we will study that one. Again, these are the book covers where this particular technique has been applied. From these titles, you can find out not only in antenna engineering, ANN technique has been applied to industrial applications like healthcare, medicine, biology, material science, manufacturing. Almost all engineering branches, you will find the application of this artificial neural network technique. Okay. Another technique is what is known as fuzzy systems or fuzzy logic. So in contrast to crisp logic, having only two stages, 0 and 1 stage or 0 and 1 value, but in fuzzy systems you can have a level which lies between these two. So as far as this example is concerned, you have a tall and a short, but unless you have a standard with you, you can't say whether it is tall or short. So you need to have some other similar thing with you to find out the height of the person. So like this one, one is tall and another is short, but given this particular problem, if the short is there, then you can say this as tall. If this particular tall is there, you can tell this particular figure as short, right? So to solve this type of problems, fuzzy logic was introduced, and you will find a lot of application of this fuzzy mathematics in antenna engineering also. Okay, now let us see the characteristics of this ANN and fuzzy logics, right? Then we will go for the other discussions. As far as ANNs are concerned, artificial neural networks are concerned, this provides an efficient alternative to closed form expressions. Fitted lumped element models and lookup tables. Because in antenna engineering, in most of the cases, we are looking for the availability of closed form solutions. What is the beauty? You just put the values of parameters, directly you will get the results in closed form solutions. Or in lookup tables, from the lookup table, you just see where your parameters are fitting, and from that you can find out the solution. These models, the ANN models, can be as accurate as the results used for driving ANN models. So those who have the basic idea about artificial neural networks, you must be having the knowledge that to train these networks, we need initial data sets, right? So the accuracy of the response of a neural network will depend on the accuracy of the data that you have used for training these networks. Furthermore, given an existing model, these ANNs can be used to update or improve the accuracy of the present model, right? If already you are having an ANN model, you can use these techniques to improve their accuracy. So just briefly, let us discuss the capabilities of this networks. Then we will go for its applications. As you know, these are neuroscience-inspired computational tools, and you can train these networks to perform a particular task. So in antenna engineering, we are basically training these networks either for analysis of the antenna or for design of the antenna, right? So if you study the initial literature of the ANN for antennas, you will find most of these applications were for analysis purpose, but gradually people used those techniques for design of antennas also. It generalizes automatically as a result of their structure, right? The training process that you are applying for training of these networks, because of that it memorizes certain things, and for new questions or for new inputs, these trained neural networks are capable of giving proper answers. The only thing to note down in this particular case is the response time of these networks is very fast. This is one of the major reasons why people are going for application of neural network techniques in antenna engineering. Okay. If you have an RF simulator, you will find that each of these simulators are having their own computation time. They take their own computation time. Okay. And this particular computation time, it increases with increase in complexity of the structure, right? But prior to the existence of these simulators, people were applying the rigorous formulation to find out the different parameters for the antennas, right? In those cases, the computation time was very huge. So to get a single parameter, single result, like hours of computation time were needed to find out a single parameter of the antenna. So in contrast to that, to avoid those large computation time, people started using this neural network techniques. In MATLAB, you can find nowadays you can find the ANN toolboxes, but again, the advice is better you write your own code for the ANN. Lot of standard ANN books are available. Lot of standard ANN training algorithms are available. So you write your own code so that during the computation process, you will find what exactly is happening, how the network is getting trained for a particular task. So what exactly is happening inside that, and how to get correct result from a trained neural network, those particular things, those particular ideas you can get only when you write your own code for neural network. These are not very large programs. Simple training algorithms are available. You just implement that and write your own code, and in each step you observe what exactly is happening, so that you will get a better idea how to approach towards the actual result. Instead of see, initially when you are starting the use of neural network, you can go for those toolboxes, but my advice is better write your own code for the neural network when you are planning to use neural network in antenna engineering. Although these techniques have their own uh, drawbacks, like generation of training data, because particularly in electromagnetics or microwave engineering or antenna engineering, it is very difficult to get proper accurate data, and you need uh, training data for training the neural networks. So this is one of the demerits of this ANN technique. And another thing is there is a possibility of getting overfitting results. That means the network will just memorize a few points, and it will give you the answers according to those particular points. That is what is known as overfitting. So somehow you need to overcome this overfitting technique, overfitting process of neural network training process. How much more time I have for this first session?
Sir, it is 10 to 11:30, sir.
Okay. What's the time now?
11, sir.
Okay. Okay. So a single neuron, we are not going through the details of that one, but it's just mimicking the natural neuron, and these are the general activation functions that we are using. But because most of these antenna problems are nonlinear in nature, that means the relationship between the output and input it's nonlinear. So better to use this last one, the sigmoidal transfer function, in most of the cases. And the computation process of a neural network is it starts with the input layer of neurons. It progresses with from one layer to the other layer, and finally you are getting the output from the output layers. So you can see that sigmoidal transfer function has been used for the hidden layer neurons, whereas for output layer neurons, better you take linear transfer functions. Okay, so that you can have, because if you are taking the sigmoidal transfer function for the output neurons, the problem is that you need to squeeze the data to remain within that particular range, -1 to 1 or 0 to 1. Then after getting the neural network output, again you need to expand that particular data value. So instead of that, to avoid this scaling problem, better for output neurons you take linear transfer function, whereas for the hidden layers, better to take sigmoidal transfer function. because most of these antenna problems are nonlinear in nature. So what exactly we are doing in this neural network training? Okay, you have this training data. So that training data can be generated. If you have an RF simulator, you use that one, create your training data, or if you have measurement facility, exact measurement facility, better use those measurement facility to create the data. Okay, then use that data to train a neural network. The variable here is X, here you are getting Y from the neural network, and in this particular case the variable is X, and you are getting the desired data value D, right? So what basically we are doing, we are minimizing this particular function, the difference between Y and D with respect to this variable. Okay, so in that way, how you are minimizing that? With respect to this W and V. W and V's are the weight values connecting different neurons of the neural network. Okay, so even if you are using the toolboxes of the MATLAB or other mathematical simulators, then once you found that you have a better trained network, then in that particular case you store this W and V values. You store in these weight values of your network, so that and after storing this these weight values, for whenever you are using that network, you use those set of weights. You use those set of weights for finding out an output of that network. Otherwise, what will happen, each time you are running the network, you are going to get a new set of weight values, and each time you have to run that particular training process. Each time you have to run. So in order to avoid that one, better store, once you have a complete trained neural network, you store those weight values, and whenever you are whenever you are trying to find out a solution of your own problem, use those set of weights. So the most widely used neural network is multi-layer perceptron. Okay. Now, when you are applying these neural networks to find out the solution of antenna problems, there are a few typical questions that usually comes into mind. How can a neural network represent an arbitrary nonlinear input-output relationship? So the answer is, given enough hidden neurons, a 3-layer perceptron can approximate an arbitrary continuous multidimensional function to any required accuracy. Although in literature, you will find neural networks with more than one number of hidden neurons, but if you see the neural network literature, it has been mentioned that if you have you take a single hidden layer, and in that single hidden layer, take sufficient number of neurons, then it can approximate any arbitrary continuous multidimensional function, right? So there is no point of taking multiple hidden layers in a neural network. So in most of these antenna problems, you will find mostly a single hidden layer. Then the question is, how many neurons are required when I am saying sufficient number of neurons in the hidden layer? See, as the number of neurons in the input layer and output layer are problem dependent, right? You see how many parameters are there. You take that many number of neurons in the input, and you see how many outputs you are requiring. Depending on that, you take that many number of output neurons. But question is how to choose the number of neurons in the hidden layer. Okay. So mostly it will depend on the degree of nonlinearity in the original problem. Highly nonlinear problems need more neurons, whereas more smooth problems need fewer neurons. Again, if the number of neurons in the hidden layer is more than the required number, then it may lead to overlearning. And if it is too less, then it will not represent the problem well enough. So what is the solution for this? Mostly, if you train more and more number of networks, neural networks, from that experience, roughly you can find out the required number of neurons. It will mostly depend on the experience and trial error method. But the approach is better you start with a few number of neurons, then you apply the training process, and gradually you go on increasing the number of neurons in the hidden layer. You start with suppose 5 or 10 neurons, then if you are not getting proper results, then increase another 2-3 neurons, then increase another 2-3 neurons, and so on. Okay. So in that way, you can have a good trained neural network. Second question is, how many layers are required, right? So as I told you, a single hidden layer is enough, but when you are taking single hidden layer, sufficient neurons has to be there in that network. So 3 or more layers are necessary and sufficient for arbitrary nonlinear approximation. And in most of the problems, you will find 3 layers only. 3 layers means 1 input layer, 1 output layer, and 1 hidden layer. In few problems, in few antenna problems, you will find 2 different hidden layers. More layers allow more effective representation of hierarchical information in the original problem. Where you want to, where you can take more number of layers, if your problem is having number of different steps. Number of different steps means the output of one step you are applying to the other step, and the output of the second step you are using in third step, and so on. In that type of scenario, you take more than one number of hidden neurons. Otherwise, it is always advisable to take single neuron, single hidden layer with sufficient number of neurons in that. We are not going to the details of this training of neural network. Those things are already there in the literature. You will find a lot of literature on training of neural networks. But another thing to see is when you are generating data, particularly in antenna engineering, because it is very difficult to get proper data in antenna engineering. So the question is, where data should be sampled? Okay, so if it is a three-dimensional problem, x1, x2, x3, better you take your sample data or training data in a uniform grid distribution. That means you take your training data after fixing the range for all the variables x1, x2, x3. You take the data at equal interval, right? So that you will find if you are taking your data in this particular manner, you will find that the training usually it takes less computation time if you have chosen your training data in this particular way. So there are two different types of training methods are available, online and offline. So it's better to go for online mode of training. That means you update the weights. Weight update is based on training error from that particular sample. Okay. As far as training of neural network is concerned, as I told you in my earlier slides, basically we are fixing the weight values of the network so that for the same input you can have a output which is almost matching with the desired result. So the most widely used training algorithm is the back propagation training algorithm, but you can have other training algorithms. Nowadays, a lot of training algorithms are available for training a neural network. The flow chart for showing neural network training. But here, one thing to mark is while collecting data, you don't use all the data for training purpose. You keep some data, some typical data for testing the accuracy of the trained neural network. Okay. So instead of using the same training data for checking the accuracy of a trained neural network, better you check that accuracy with some new data values so that you can find out whether the network was trained properly or not. So to give you an example of this ANN application, although this particular thing we have done long back, but to get an idea how to use ANN for design for microstrip antennas. See, is a simple rectangular microstrip antenna. You need to find out the dimension of either the rectangular or the circular page. So for example, if you want to find out the radius of this circular page antenna for the antenna to work at a particular frequency, what are the steps? First, you need to choose the different variables, range of these variables, like depending on the type of substrates that are available in the commercial market, you choose the value of height h. Then your epsilon r can have minimum value 2, maximum value 10. Then this radius, depending on the frequency range in which you want to have an ANN model, you choose the value of this radius of this circular page. Okay. Now see this one. This is a closed form formula, right? To find out FR, resonant frequency. This particular formula can give you a reasonable good result when you are trying to find out FR, resonant frequency, given these parameters. But that's not a problem. The problem is, suppose I want to find out I want to design the antenna, or I want to find out the radius of this circular page for my antenna to work at a particular frequency. So if I try to use the same formula to find out that particular information, you can mark that on the right hand side, you have one A here, another A here, here one A, and so on. So if I try to find out this A or the radius from this particular formula, then it will end up with a iterative equation, and you know what are the demerits of iterative equation. So instead of that, what I can do is I have that particular model or that particular formula where I can give epsilon r, h, and the diameter or the radius. Then from that I can find out FR. But to the ANN, what are the things that I am giving? Epsilon r, h, and the FR as the input, and I am finding out the radius of the patch. Okay, and this can be compared with the radius or the diameter I am getting from the actual formula. Okay, that particular data I have already generated. So from this error can be minimized by the training of the neural network. So from that way, I can find out the radius. So you can mark from this figure for typical set of this epsilon RH, the page radius results for different resonant frequencies are exactly matching with the frequency that you are finding out from using that particular formula. So this is a typical way of applying neural network technique. So the advice is, where you have a closed form formula available, don't go for applying neural network technique for that. You just apply that closed form formula and get your result. But as discussed in this particular example, because finding out the radius from using that particular formula, it gives rise to an iterative equation. So in order to avoid that particular iterative problem, you can opt for a neural network. Okay. The comparison results. Okay. So some issues of using neural network, the problem in hand can either be implemented in total or a part using neural networks. So the entire problem can be implemented in neural network, or there are situations where for a part of that problem, you develop a neural network and other parts can be used as it is. Right? So in both ways, neural networks can be used to solve antenna problems. You can find some problems implemented entirely using neural networks. Some problems, a part of that has been used has been implemented in neural networks. Okay, so any questions at this particular point? I will stop for a few minutes at this point, then we will start the new session.
Sir, I have one doubt,
Sure.
sir. So, what is online and offline training of artificial neural networks, sir?
In offline training, suppose you have 100 training data sets you have created. So you apply one after other, you find out the total error. Based on that error, then the next set of weights will be decided after calculating the total error that you are getting out of all these 100 data sets. Okay, so basically in training of the neural network, your job is to update the weight values, weights connecting different neurons. Okay, so if you are updating that weights, which is based on the error of all the data sets that you have created, that is called offline training. And if you are updating the weights after applying each data set, that is called online training.
Okay, sir. Thank you.
Yeah.
Sir, I have one more doubt, sir.
Sure.
How can we get that data set while designing, sir, while training artificial neural network, sir, for antenna design?
Yeah. As I told you earlier that, see, if you have an RF simulator, see, simulators have their own, they take their own training time, simulation time, right? So it will depend on the complexity of your antenna design, complexity of the problem. If it is a more complex structure, it will take more amount of simulation time. So if you have an RF simulator, from that you find out the training data, you generate your training data. That is one method. Second method is, if you have measurement facility, you vary the parameters of the antenna, measure that antenna, and store those measured results. You can use that also as your training data. Third method is, you study the literature. In literature also you will find a lot of published data available. So you store those published data, that also can be used as a training data.
Okay, sir.
Okay.
Okay, sir. Thank you, sir.